Hi, this is Woo-Jae Kim from KAIST. In this video, we present our paper, Diverse Generative Perturbations on Attention Space for Transferable Adversarial Attacks. This paper presents a new way to improve transferability of adversarial attacks by generating diverse perturbations that disrupt image attention. While a deep learning model has been shown to be promising in numerous computer vision tasks, it has also been known to be vulnerable against adversarial attack, which is a perturbation applied on an image such that it is maliciously designed to fool machine learning models. As shown in this figure, a deep learning model can classify this image of a cat as a cat. However, we can perform adversarial attack on this image to craft this adversarial image. This adversarial image still looks like a cat to human eyes, but a model misclassifies this image as a dog. It has also recently been known that these adversarial images crafted on a known white box surrogate model can also sometimes fool unknown black box target models. This characteristic is known as the transferability of adversarial attacks. In a real-world scenario, the information of a model, including its weights, structures, and gradients, are usually hidden from the attacker. In this scenario, transferability allows an attacker to craft adversarial examples on a known model to also fool unknown models. However, most of the existing white box attacks usually suffer from limited transferability because they are often overfitted to the surrogate model. Due to the difference in structure and weights across different models, these attacks usually fail to transfer to other models, making them suffer from poor transferability. To this end, numerous attempts have been made to improve the transferability of adversarial examples. However, these attempts have mostly relied on a gradient-based method, which greedily steps towards maximizing the given objective at each iteration. Thus, they inevitably craft adversarial examples in a deterministic manner and easily fall into a poor local optimum. As shown in this figure, this makes the adversarial examples become overfitted to the surrogate model, in which case they would fail to transfer to different target models. To avoid such poor local optimum and overfitting to the surrogate model, we propose to guide the attack to fool the model in a diverse manner. As shown in this figure, this will make the attack explore the search space of adversarial examples more exhaustively, and thus prevent the adversarial examples from falling into a poor local optimum. Adversarial examples generated this way are less likely to overfit to the surrogate model, making them successfully transfer over to different target models. To achieve this goal, we propose the Attentive Diversity Attack Framework, or ADA in short. In this framework, to prevent deterministic attacks caused by gradient-based methods, we design an attack generator to craft adversarial examples. Given a natural image X and a latent code Z sampled from a Gaussian distribution, the attack generator G generates an adversarial perturbation. This perturbation is added to the natural image and clipped to the perturbation bound epsilon to obtain the adversarial image. Through latent code Z, we aim to learn the attack generator to craft diverse perturbations given different latent codes, thus avoiding poor local optimum. To train the attack generator to craft adversarial examples that can fool both the surrogate and target models, we train it to disrupt the image attention representation. Recent works have shown that attention of a model is likely to be shared across different models. This is because while these models have different weights and architectures, they tend to focus on similar regions on the image to make a decision. For example, all four models on this figure share similar attention representations. They focus on the head of a gorilla to classify this image as a gorilla. Based on this intuition, we disrupt the attention representation of the image. Since different models share similar attention representation, disrupting attention of the surrogate model will also disrupt attention of the target models and mislead their final predictions. We calculate attention A, given image X and ground truth label T as follows. We first obtain the gradient of YT, which represents the model prediction output for ground truth class T, with respect to the target feature F. Then we take global average pooling on the gradient and take element-wise product between the output and the feature representation F. In other words, we treat the weighted feature representation as attention, where the activation of channels that are important to model prediction are boosted, while activation of channels that are less important are suppressed. Then we design the attention loss as the L2 distance between the attention representation of the adversarial image that is crafted by the attack generator and the attention representation of the natural image. Then, the attack generator is trained to maximize the attention loss. As shown in this diagram, the generator is trained to craft perturbations that lead to different attention representations from that of the natural image, thus fooling both the surrogate and target models. However, without any guidance, the attack generator may disrupt the attention in a deterministic manner. In other words, it may simply ignore the latent code Z and generate the same perturbations for different latent codes, which will then make it fall into a poor local optimum. Thus, we explicitly guide the generator to disrupt the attention differently given different latent codes. To achieve this goal, we propose the diversity loss, which is formulated as follows. Given the same natural image, X, we sample two different latent codes, Z1 and Z2, and generate two different adversarial examples, X-ADB-Z1 and X-ADB-Z2, using the attack generator. Then, we obtain the attention representation for the two adversarial examples, and we design the diversity loss as the L1 distance between the two attention representations regularized by the L1 distance between the two latent codes. We then train the attack generator to maximize the diversity loss. This guides the generator to produce different perturbations for different latent codes, such that they lead to adversarial examples that fully model attention differently. In this way, the generator exhaustively explores the search space of adversarial examples and avoids falling into a poor local optimum. Given the attention loss and the diversity loss, the overall objective of the framework is to learn the generator to maximize both loss functions. We control the weight of each loss using two hyperparameters, lambda attention and lambda diversity. Now, we would like to share some of the main experiment results. We first report the comparison of attack transferability with existing transfer-based attacks. The leftmost column shows the surrogate models used to craft adversarial examples, and the uppermost row shows the target models used to test attack transferability. We use the attack success rate, which is simply the misclassification rate of the models, to compare transferability of the attack. We make comparisons with the existing method, which all rely on a gradient-based method. While our method lags behind the existing methods on the white box attacks marked in parentheses, which is when the surrogate model is the same as the target model, our attack outperforms existing methods in most of the black box settings. This shows that our method overfits less to the surrogate model and generalizes well to the unknown models. Also, one interesting observation is that our method outperforms existing methods by a larger margin when the architectures of the target models are more different from that of the surrogate model. For example, while our attack crafted on Inception V3 outperforms FIA by 4.7% point on a more similarly structured Inception V4, it outperforms FIA by a larger margin of 9.6% point on a more differently structured VGG16. This shows that while existing methods overfit to the surrogate model and show low transferability on models with more distinct structures, our method still generalizes well to these models. Now we show that our method can indeed generate diverse adversarial perturbations. Recent findings have shown that the robustness of adversarial training model improves when trained against a diverse set of adversarial examples. Based on this finding, we adversarially train a model against different gradient-based methods, including FGSM, BIM, and PGD, and also our method with or without diversity loss. As shown in the table, our method with the diversity loss shows the highest robustness against all adversarial attacks. While existing gradient-based methods and our method without diversity loss train the models only against a limited set of deterministic attacks, our method with the diversity loss trains the model against a diverse set of adversarial examples and makes it more robust. We now show that diverse adversarial examples generated using our method are indeed more transferable. The two figures show the PCA visualization of the features of adversarial examples crafted by FIA, which are shown in blue markers, and our method, which are shown in red markers, on the surrogate model, or Inception V3, and the target model, which is ResNet V2. FIA generates deterministic adversarial examples whose feature representations form a dense cluster, while our method generates diverse adversarial examples with a wider distribution. On the surrogate model, we can observe that FIA generates stronger adversarial examples. The average altitude distance from the feature of the original image, marked in black circle, to the features of the adversarial examples crafted by FIA is a lot larger than the distance between the feature of the original image and the features of the adversary examples crafted by our method. However, in the unknown target model, the distance to FIA adversary examples is a lot smaller than the distance to adversary examples crafted by our method, showing that adversary examples by our method are stronger in the black box setting. This shows that our method generates highly diverse adversary examples that also show higher transferability on black box target models. We also verified the effectiveness of our two proposed objectives, or the attention loss and the diversity loss, by controlling the weights on each term. We used Inception V3 as the surrogate model, and in general, those objectives play an important role at boosting the transferability. We achieved the best performance when lambda attention is 10, and when lambda diversity is 1000. Interestingly, the attack success rate against Inception V4 is higher when lambda attention is smaller at value of 1, and when lambda diversity is smaller at value of 100. This is because insufficient weights in the two objectives overfit the attacks to the surrogate model and lead to higher transferability on a more similarly structured Inception V4, but reduces transferability on more differently structured black box models. This chart shows that our method can outperform existing approaches under various perturbation constraints epsilon, which controls the magnitude of adversarial perturbations. Even at lower epsilon values of 4, 8, and 12, our method outperforms existing approaches with a significant margin. Finally, we visualize the semantically diverse adversarial examples crafted by our method. We show 5 adversarial examples crafted using our method with different latent codes. For all 5 images, the model misclassifies each of them to different classes, and also infers different attention heat maps, showing that our method indeed disrupts the model in a diverse, non-deterministic manner. Thank you for watching our project video, and please feel free to visit our project webpage and code repository through the QR codes on the screen.